Hello everyone, I'm Adrian. In this work we ask the question how the intrinsic compliance of Dexterous soft hands can support the automatic generation of in-hand manipulation skills. In prior work we demonstrated that the compliance of soft hands contributes immensely to the robustness of in-hand manipulation skills. For example, in this video all of the objects are manipulated successfully with the exact same open loop action sequence. No sensing involved. So, how is compliance contributing? In the following plot, you can see the optimal actions for a given manipulation task over time in green. In case of a rigid hand without any intrinsic compliance, the controller needs to deal with all the complex contact dynamics explicitly. Therefore, actions need to be taken that stay within the gray tunnel in order to succeed. If we add appropriate compliance to the system, this tunnel widens, which reduces the responsibility on the control side because the set of possible good actions increases. We will leverage this characteristic to automatically generate in-hand manipulation skills. We show that simple linear feedback control based on Jacobians is sufficient for this purpose. For control, we can use roughly approximated Jacobians that we obtain from explorative actions. We only need to make sure that we stay within the compliance tunnel. In addition, this tunnel allows us to reduce the control frequency and to take large actuation updates. Of course, we need a control quantity that is appropriate for our control scheme. In the paper, we introduce the deformation state as well as the deformation Jacobian of a soft hand. The deformation state is simply defined as the difference in available sensor measurements when the hand is in contact and when it is in free motion. To test our control approach, we use the Dexterous soft RBO hand 3. The hand is equipped with strain sensors wrapped around the soft fingers and bend sensors placed in the compliant joints of the thumb mechanism. These sensors are used to measure the deformation state. Now, I'm going to show you how compliance allows us to generate a robust manipulation skill within a minute. First, we obtain a control target through demonstration by simply placing an object inside the hand and moving it in the desired way. In blue, the undeformed position of the ring finger is depicted. And as you can see, the ring finger deforms a lot. And that allows us to reflect the object motion in the deformation of the finger that we will use as our control target. Next, the hand figures out by itself how to reach the goal. This happens through approximated Jacobians. These Jacobians can be generated on the fly based on explorative actions, in this case of the thumb and little finger. After the goal has been reached, a different skill can be sequenced, in this case an open loop finger gate. The generated Jacobians are stored and can be reused when we place the object again inside the hand. This happens with simple K&N regression based on the current sensor measurements. But what happens if we place a different object inside the hand? We start off with the set of 3 Jacobians from the last video. We see that for similar object properties, the available Jacobians are sufficient to reach the goal. For smaller and soft objects, as you can see in the second row, new Jacobians need to be obtained to fulfill the task. All of this happens online and is refining the manipulation skill. For the next execution, the extended Jacobian set can be applied to deal with these objects right away. In the paper, we show that our system can also adapt to turning the hand upside down and to failing actuators. In conclusion, the compliance of Dexterous soft hands absorbs the complex contact dynamics. Based on this insight, we proposed a simple way to generate local manipulation primitives automatically. These can be interpreted as manipulation funnels. These funnels can be traversed based on feedback and can be continuously refined as shown. Based on these properties, such primitives can serve as a building block to generate more complex manipulation behavior. In the future, we want to investigate how to autonomously learn these skills and their connectivity to use them for planning. Last but not least, thank you to our sponsors.